Water. Water is the essence of life, but how do we ensure its quality? Meet TDS meter, a simple yet powerful tool for measuring total dissolved solids. In this presentation, we will explore what a TDS meter is, how it works, and its significance in our daily life. Hello everyone, I am Himanshu Shrote from Chemical Engineering Department, enrollment number BT21 CME 030. In this presentation, we will look forward to the introduction of TDS meter, its instrumentation, its working, application, and some of the limitation. So, let's begin with the basics. Total dissolved solid. So, total dissolved solid is the total concentration of dissolved substances in the water measured in parts per million or ppm. These substances include both organic and inorganic material such as calcium, sodium, potassium, and even phosphates. But where does this substance come from? TDS can originate from the natural sources like the earth's mineral or from human activities such as agricultural runoff, sewage discharge, and industrial waste. The presence of TDS in water affects its taste, safety, and usability. Moving towards the measurements method, there are two primary methods for measuring TDS. One is gravimetric and other is conductive. So first, seeing the gravimetric method. The gravimetric method is the gold standard. It involves evaporating the water sample to remove moisture and weighing the residue left behind. While accuracy of this method is comparatively low as well as it is time consuming. So here the water is evaporated at around 103 degrees Celsius to 180 degrees Celsius and the water content is totally removed and then the remaining residue is weight. So the remaining weight of the residue is considered as the TDS or the total dissolved solid in the water. Another method is conductive method. So in conductive methods, we basically utilize the property of water which is conductivity, where the ions from the dissolved solids create the ability for water to conduct an electric current, which is measured by the IC controls, analyzers, and immediately displayed as an sodium chloride ppm or MgL conductivity. When periodically standardized with IC controls, TDS standards, or by laboratory gravimetric TDS meters, TDS analyzers based on conductivity provide a quick, accurate value of TDS. In this presentation, we won't go deep in IC controls and all. We will be looking on the principle of TDS measurement. Moving toward instrumentation parts. A typical TDS meter consists of several key components: the housing, a durable outer shell that holds everything together; the display, often LCD screen that shows the TDS reading; the electrodes, immersed in water to measure the conductivity; the circuit board processes the signals from the electrodes; the battery compartment, a power house of the device, which provides power to generate a current. Control buttons for the power and the calibration adjustment. Together, these components make the TDS meter an efficient tool for water quality testing. In some of the TDS meter, there also consist of a thermocouple due, which helps us in getting a temperature of a water, and it is also displayed on the LCD screen of the TDS meter. Moving toward the working of TDS meter, electrodes and water interaction takes place. A TDS meter has two electrodes, typically made of conductive material, which are immersed in the water sample. When this electrode is submerged, they create an electric field in the water. Ion movement and current generation. Dissolved solids in water, such as salts, minerals, exit as a charged ion, cations and anions. When the electric field is applied, these ions move. Positively charged ions move towards the negative electrode and negatively charged ions move toward the positive electrode. This movement of ions generate an electrical current in the water. Measuring the conductivity. The TDS meter measures the magnitude of electrical current flowing between the electrodes. The higher the concentration of dissolved ions, the greater the conductivity of water. Pure water, in contrast, has very low conductivity because it lacks significant dissolved ion. Conversion of electric current or the conductivity to the TDS value. Using Ohm's law, the meter calculates the conductivity of the water in the microsieverts per centimeter. The meter then applies a conversion factor, usually between 0.5 and zero point 0.7, depending on the type of dissolved soil, to estimate the TDS value in the water per million. Taking an example calculation, if the meter measures a conductivity of 1000 microsieverts per centimeter and conversion factor is zero point 0.5, then the TDS is calculated as TDS equals to conductivity into conversion factor. Then for our example, the TDS gets equals to 500 ppm. This indicates that the water contains 500 milligrams of dissolved solids per liter. Moving toward the calibration part, a TDS meter involves setting it to a known standard value to ensure accurate measurements. Here's a step-by-step guide. Obtain a calibration solution. Use TDS calibration solution with a known concentration which matches the range of TDS you typically measure. These solutions are widely available and come with a specific ppm value for calibration. Prepare the meter. Turn on the TDS meter and if needed, clean it with the water, the electrode part with the distilled water to remove any residue. Shake off any excess water to prevent the dilution of calibration solution. Immerse in the calibration solution. Place the meter electrode into the calibration solution. Ensure that they are fully submerged into the water without touching the container sides. Adjust the meter. Some meter automatically detect and calibrate this with the solution. Other have manual adjustment, screw or button for manual models. Adjust the reading to match the solution's known ppm value. Wait for stabilization. Allow the reading to stabilize, typically a few seconds. Then check that it matches the solution's specified value. Repeat the adjustment if necessary. Rinse and store. After calibration, Rinse this electrode with the distilled water and allow the meter to dry. Store in a safe place, ideally in a protective cap to maintain the calibration. Regular calibration, especially for professional use, ensure accurate and reliable TDS reading. Typically recommended every 2 to 4 weeks or after heavy use. Moving toward the application part. So, one of the most important application of TDS meter is drinking water. Ensure safe TDS level for drinking water in household and purification system. Then it is used in agriculture. Monitors irrigation and hydroponic water for optimal plant growth and soil health. There are many farms which do hydroponic farmings. In Nagpur, there is also a farm where they do hydroponic farming, where they plants the plant in the water, and they provide all the minerals through water. The water runs from the pipe, and the plant is planted on the top part of that pipe. Then it is used in aquarium to maintain proper TDS of aquarium water is important. Water quality for fish health in aquarium and aquaculture is done by TDS meter. Industrial use prevents scaling and equipment damage in boilers, cooling system, and food processing. High high amount of TDS in the boiler water or a cooling system water or heat exchanger might lead to the fouling of the equipment, making the heat transfer more resistant. So, proper TDS of the fluid or the liquid inside this equipment is important. Then, environmental testing. Monitor natural and wastewater quality for pollution control and compliance. Then, educational lab. Supports water quality analysis in chemistry and environmental study. So, in educational labs, TDS is also important as there are many scientists doing researches, so they need distilled water or water with the proper TDS. So, in that system, the TDS meter plays an important role. Then, moving towards some of the limitations of TDS meter. Measure only ionic solid. TDS meters only detect electrically charged ions such as salts and minerals, not non-ionic dissolved substances like sugar or oils. Limited specificity. TDS meters provide a total concentration of dissolved solids but do not identify the specific contaminants such as heavy metal or specific minerals affected by temperature. Conductivity and therefore TDS reading vary with the temperature. So without automatic temperature compensation, result can be inaccurate, not a direct health indicator. High or low TDS reading do not necessarily indicate how harmful or safe water quality is, as some dissolved solids are beneficial while other may be toxic. Influenced by water type, conversion factor which we used in our formula vary based on the water composition. So, standard setting may not be accurate for all types of water, cannot detect bacteria or organic. Since TDS meter only measure dissolved solids, they cannot detect microbial contamination or organic pollutants, requiring additional testing for complete water quality assessment. Thank you for listening the presentation. If you have any doubt or a query, be free to comment down. Thank you.